The last application to look at, I guess, is in the finance area, and this is more with geometric series rather than arithmetic one, but it actually is very useful. The first sort of finance formula, I guess, you see is not a realistic one when you think about it, and that's simple interest. Of course, simple interest was simply, PRT. So I being the interest, P being principal, R being our interest rate, T being the time periods, and we simply said, I'm going to give you, 5% for 10 years, and you said, what's 5% of that times 10? And we worked it out. Or, in fact, here's a different example. 3,000 invested at 6% for 7 years. And so you're simply basically going PRT. But, as I say, what you're really doing is you're just finding 6% of the amount, timesing them by the number of years and saying, that's the interest. That's not how interest works in reality. So that's why they call it a very simple interest formula. It's a very simplified idea of how interest actually works. Of course, compound interest is how we work in the banking industry because, of course, once you earn interest, that's your money, and then they've got to pay interest on that money now. So it's interest on interest, hence the compounding. There's the compound interest formula, and hopefully you can see the link with geometric series, because essentially it's just the general term of a geometric series when you write it like that. Now, amount n, so it doesn't just work out the interest, it works out the total amount. P is our principal, but R is not just the interest rate, it's how it's growing. So it's 1 plus the interest rate. And n's the number of times. The important thing is, though, when you're using this formula, is that your interest rate and your time periods are measured in the same amount. So per year, per month, whatever it happens to be. So we do that same question, but now we're doing it with compounding interest. So PR to the power of n, 3001.06 to the power of 7, it grows to 4,510.89. So the actual interest was... what did we start with? 1,510. Yeah, you see you get a little bit more. So if we went compounded monthly, 7 years would be...
84.
Thank you, 7 12s or 84. So we'd use power of 84, but notice the interest rate I've used there is 0.5% rather than 6%, because it was 6% per annum. But again, you get slightly more interest when you compound it that way. So in fact, when you are investing, or even borrowing money for that matter, ideally you want the interest to be done in smaller and smaller amounts. Because it'll grow, quicker and quicker. Now, depreciation is basically the same, because it's still PR at the end, but now instead of adding on interest rates, you're subtracting a depreciation rate. So it's still like a geometric series. An espresso machine, which is a coffee machine, they tell me. I don't like coffee myself. And they're quite expensive. $15,000. 1st of January 2001 is when they bought it. Depreciates very quickly at 12.5%. How much would it be worth on the 1st of January 2010? So that's after how many years?
10.
So let's see. 9. Because if you're starting 1st of January 2001, it takes you 9 years to get to 1st of January 2010. You can see in that time, in those 9 years, it's depreciated down to $4,500. Loses value quite quickly. So when will it drop below 10% its original value? So 15,000, so an exponential inequality to solve here. Or we've got to divide, bring the n in front, divide by log 0.875, but 0.875 would be... So if you...
Flip the side. Change the side. Oh, that's blasphemy.
Change the side. So n is greater than 17.24. So it'll be the 18th year, which is 2018. Because the first year is 2001, second year is 2002, so the 18th year, sometime in that 18th year, it will become 10%. Now, Where it gets really interesting for HSC questions is when we take that idea of compound interest and repeatedly apply it. So regular instalments. Again, it's a very simplified version of superannuation. In superannuation, you tend to put regular amounts in. In reality, you don't get a consistent interest rate all the way through because, well, interest rates change over time. But for this modelling, we assume the interest rate's the same all the way through. So here's our superannuation fund. We're assuming 8.75%. And we're going to invest $5,000 at the start of each year, commencing 1st of January 2003. So this HSC question, you'll notice, was in 2002. So what will be the value when she retires? 20 years? Gosh. Most of us end up working more than 20 years before you can retire. But anyway, on the 31st of December 2023.
20.
Okay. 21. 21 years. So that first investment, that investment you make has been in the bank for 21 years. Okay, good. The next year I'm going to put another $5,000 in, or Stephanie is anyway. And that amount will be in there for 20 years. Then the next year, but that'll only be in there for 19 years. And so on and so on and so on, until we get to the one on the 1st of January 2023, which will be in there for 1 year. That's why it stops on the 31st of December, because it's not like we're now going to give them $5,000 and then go, no, I'm going to take it back. And it's in there for 0 years. So that's why they say 31st of December rather than 1st of January 2024. So we've got all those amounts earning interest. So you can see we've got a series there. Okay. So we can say, well, the first term is 5,000 times 1.0875. The ratio is 1.0875. The number of terms there is 21. So in other words, we just say, oh, it's the sum of 21. So we can put in our sum to end formula, and our total investment has become $299,604.86, and Stephanie thinks she's going to retire. So I'll put an asterisk there because this question wasn't actually in the HSC, but I thought it'd make it a little bit more interesting. So when will the fund first exceed $200,000? So we want to know, when is that sum? So we now want to know what N is, not the time of day, just which year would be good. Sum to N. We want to know when it's greater than 200,000. So again, it would be our sum to N, but now we just don't know what N is. We want to be greater than 200,000. Playing around with those numbers, actually, it works out quite nicely. That fraction's just 280 on 87. In this case, it's a log of a number bigger than 1,
So it's fine.
so we don't change the sign. And we get 17.1. Oh, this is going to be fun. So we know when N is 18 because we don't round down, because if N is 17, it hasn't reached 200,000 yet. Next question, which instalment, right, because obviously putting in $5,000 only produces that 200,000. We want $1 million by the 31st of December 2020. So we now know that it's going to be in there for, this time we don't know how much to invest. That's what we want to work out. So we want to know when sum 18 is going to be $1 million. P is what we're trying to work out. There's the amount. Plug it into our calculator.
Oh, okay, I get it.
A little bit more than she had decided to invest. So $23,000 each year. Now we can do loan repayment. So now we're repaying money. Right, we're borrowing money and got to pay it back. Now, the key to this is what we are interested in is the amount that's still owing after a number of time periods. So we'll call that AN, but it's always going to be the principal that I borrowed with the interest applied minus my repayments with the interest applied. Okay? That'll always tell me how much I've got owing. Okay, here we are. Richard and Kathy are going to borrow $20,000 to go on a holiday. Interest is 12% per annum. Personal loans tend to be more expensive, so 12%, probably a bit high at the moment, but compounded monthly. They start repaying the loan 1 month after taking it out. So again, similar to the investing, you don't borrow money and pay back straight away because that would be silly. Can I borrow some money? Thanks. Here's your first payment. Doesn't make sense. All right, so it's always one time period after you start borrowing. And the monthly instalments are going to be $300. Okay. How much will they still owe the bank at the end of 6 years? 72, because we're talking about months. Right? So the initial loan will be in there for 72 years. Right. 72 months, sorry, not 72 years. Yeah, so, okay, so the principal plus interest will be $20,000, 1.01. Fortunately, they gave me a nice number to work with. 12% per annum is 1% per month, to 72. Okay, so the repayments you've got to think of like an investment. It's like a reverse investment. It's like the bank borrowing off me. So my first repayment, because what we're saying is the contract is going to end, in this case, after 72 months we're interested in. So I'm going to give them some money, and they're going to have that money for 71 months. My first repayment. So that's why we apply the interest for 71. My second repayment they will have for 70 months. And so it's just like that investing. My second last repayment, though, in this case, will be there for 1 month. Because in this case, I will, on the very last day, give them my last repayment. So that actually will be in there for 0 months. Because I'll give them $300, we'll say, thank you, our contract's over, done. I've paid back everything I have to pay back. But again, we end up with a series here, as far as the repayments go. So amount 72 will be the principal plus interest for those 72 months, minus all of those repayments a month at a time. And so in the second parentheses there, that's where the geometric series is. So the first term's 300, the rate's 1.01, number of terms 72. And subbing in then, it works out that we still have $9,529 to go. So how much interest have they paid in those 6 years? Right. We've made 72 repayments of $300. That's $21,600 we have given the bank. But I still owe them $9,529.01. So in fact, I've only taken off $10,470.99 off what I owe them. The difference between the two must be the interest that I've paid. Which is, yes, you see, quite a significant amount. Remember how much I borrowed?
20,000.
And so after 6 years, I've already given them an extra $11,129. And home loans are like that, even though interest rates are quite small. Because they're taken out over such a long time period, you end up paying a lot of money in interest. So what about if the problem was I want to work out how much to pay back? Because I know, okay, I want to pay it off in so many years. So here's one. Yog wants to borrow $30,000. I don't know what the monthly instalment is now. I'm just going to call it M. So the initial loan will be borrowed for 60 months. So that principal interest rate applied. My first repayment of M, whatever it is, will be in there for 59 months. Then the next one for 58 months, and so on until I get to that last one, which will be in there for 0 months. So I know the amount N will be the principal with the interest applied minus all my instalments. So there's my formula, amount 60, but of course I know what amount 60 is. 0, because that's when I want to pay it off. Now A is M, R is 1.0075, N is 60, so I can sub that into my formula. All I really got to do now is make M the subject of this. So that's 0, playing around, eventually, where's M? Oh no, keep going. M is that amount there, but a bit of number crunching to work it out. Turns out to be $622 a month. Oh, and 75 cents is what I'd need to use. What about if we know how much we want to borrow and how much we can pay back? In other words, we want to find out, well, how long is it going to take us to pay off this loan? Now, obviously they borrow large amount of money. They're borrowing $3 million at the beginning of 2005, 12% interest each year, calculated balance at the beginning of the year, added to the balance owing, the debt by equal annual repayments. So just going to give them one payment a year, and it's $480,000. The first repayment, just to be clear, will be at the end of 2005. So at the start of 2005 they borrow, they pay their first one back at the end of 2005. So let AN be the balance owing after N. Now, the first question was simply show that the amount owing after 2, although they didn't say it like that, they simply said show that A2 equals this expression. But A2, of course, is the balance after 2 years. So it's only 2 years we're considering. So the initial loan, if we borrow for 2 years, $3 million, interest rate applied. We'll have one repayment. It'll only be in there for 1 year because we're saying after 2 years. And so then that second repayment, and that's it. And we're saying the amount owing will be the principal with the interest applied minus the repayments with the interest applied. So if we sub in, we have in fact got what they want. They've just written it in scientific notation. 3 million is of course 3 times 10 to the 6. Common factor there of 480,000, which is 4.8 times 10 to the 5. So there we go. So I suppose that might have been hopefully a gift mark at the start of the question. All right, they now want us to come up with a general formula for amount N. So, all right, we don't know what N is. So the initial loan, 3 million, interest applied for N time periods. The first repayment, therefore, would be there for N minus 1 years, then N minus 2 years, and so on, and eventually we'll get to that last repayment, which will be there for 0 years. So principal with interest minus instalments plus interest. And there's our expression. We've got a series there. First term's 1, ratio is 1.12. Number of terms is? N. Yes, not N minus 1. So N is, strangely enough, N. Well, we've got to come up with this expression, 10 to the 6. If we sub into our geometric formula, our sum to N terms, okay. Now, they were nice because actually 480,000 divided by that 0.12 comes out to be a very nice number of just, what's that, 4 million. 4 million. Yeah, okay. So that gives us negative 1 million. So we've got that. Again, they use not scientific notation. They've factorised out the million and made it 10 to the power of 6. Well, I suppose it is sort of scientific notation. They just haven't gone 1 times. So 10 to the 6. Okay, we've got the formula they wanted us to prove. So the last bit of the question, in which year will Wheeler Barabak, Shire Council, make the final repayment? So in other words, when will amount N equal 0? So we just have to solve this little equation. Divide both sides by 10 to the 6. Exponential equation. So we'll log both sides. We can bring N to the front. Divide by log 1.12. Log 4 over log 1.12 turns out to be 12.2325. So during which year? So the 13th repayment. So remember, they're paying in lump sums. So when they make the 12th repayment, they still owe some money. The 13th repayment, it won't be a full repayment. 7B, 7C, 7D. I think you'll find 7D's on the repayments. 7C's probably on the superannuation. So 7B's probably just simple interest, compound interest maybe? Trying to remember. It's probably something logical like that.